Fred's an expert in biopolymers, and so he's going to take us through some of the big advances that have happened, actually a lot of them due to him, in our understanding of biopolymers, both from the kinds of things that you see in actin, which are very that are located inside cells, all the way to collagen networks, probably next week, which are athermal and constitute a lot of the extracellular matrix and things that I care about a lot, like cartilage and things like that. But we're going to go from the beginning, so take it away.
I think I've turned everything on. Yeah. I do tend to be loud, so I hope someone will check to make sure I'm not saturating this microphone. I would normally not use one in a class setting like this, so anyway. Can I get a thumbs up that it's at least okay? Okay, good. And I assume online too. So indeed, what I wanted to do is introduce you to a class of interesting materials, both biological and non-biological. I'll focus on the biological examples. I'll, along the way, be moving increasingly toward things like collagen and implications for tissue mechanics. But I want to start, by the way, should we turn off some lights right near the screen, maybe? Yeah, I think that's better. Okay, so, yeah, and the pointer works, good. So, when you think polymers, I think most people tend to think of things like Gaussian chains, random coils, entropic elasticity, things like that. Hopefully that's familiar to several people. It doesn't have to be. But one of the things I want to do is reorient you, or if you like, get you to unlearn a lot of the things you learned about flexible polymers and look at a class of systems of which there's many non-biological examples, but which I think both historically and also in terms of importance and level of study over the years, the biopolymer systems are probably the best example. So you might not have realized it, but a fundamental building block for a lot of us and biological systems generally are polymers and networks of polymers. And immediately I should contrast with the polymer that might come to mind when you think about biology, namely DNA. DNA has an informational role primarily. I'm talking about biopolymers that have structural roles. And in fact, elasticity, subject to this school, of course, is going to play a prominent role, and I'll be showing you some phenomenology having to do with elasticity of these systems. But already inside individual cells, so this is just a I guess it's not attributed, but this is the kind of thing you'll see on Wikipedia. I think that image is taken from Wikipedia. It's a, I think, epithelial cell, but I'm sure someone who knows more about the biology could correct me on that. But it's a typical, not particularly specialized cell, and in particular, I mean not a muscle cell. So muscle cells tend to have a much more ordered polymeric structure. Involving the polymer that's labeled in red here, typically appearing near the periphery, at least in largest concentration in this cell. Should also give you a sense of the scale. We're talking about a couple tens of microns across, 40, 50 microns. Blue is the DNA, if you like, the nucleus. Not going to be a subject of interest for us, although it is interesting, of course. In green are labeled microtubules. Microtubules are the thing that obviously are polymers or at least filaments in this image. You can see the filamentary structure, typically organized in two ways, not just anisotropic, in this case sort of emanating from near the nucleus and extending toward the periphery. They're also polar. So this is another interesting aspect of a lot of these biopolymer systems. They're polar in a way that, if you like, involves a local arrow that says this direction is different from that direction, independent of what the ends look like. So it's not polar because of the ends. Most of these biopolymers are polar, not all. But that's the most obvious structure you see here. Typically, microtubules don't play a huge mechanical role. And I know I just offended maybe some people. They certainly can, but it's not generally the main thing they do. They typically are highways for transport. That directionality is important for something we might get to next week, molecular motors and transport along those. That's not an aspect that I want to focus on. The stuff that just shows up as sort of a diffuse red glow near the periphery is a network that zoomed in would look more like this. It's an actin meshwork. In a lot of cases, it's quasi-two-dimensional in the sense that it's sort of a cortical layer near the outside, but in other cases, it's a bulk meshwork. And already this picture, certainly that picture, even this picture, starts to suggest that this is very different from what you might think of as a textbook picture of a flexible polymer network. There's nothing like a random coil between, let's say, junctions in this network, okay? They're pretty straight fibers. Now, in detail, what these fibers really are is assemblies of globular proteins into some linear structure. In the case of actin, one of the main players, the red stuff here, and at least temporarily color coordinated here, red in this image. I'll go a little bit back and forth depending on the imaging people used in experiments. So it's actually a double helical, nothing like DNA, but you shouldn't be surprised when something's helical in biology. Everything's chiral. So it's just natural that there would be a broken symmetry in the handedness of this. But it's also polar, so one direction is different from another. You can sort of see that maybe as the sketch of a little asymmetry of the monomers making up this assembly. The fact that it's double is not essential. It just is important for the stability of this structure. But it's already huge on a molecular scale. So the diameter of this is already 7 nanometers. 7 nanometers is big for a monomer in a conventional polymer system. And they form these arrays where you can see I don't remember exactly what the scale bar here is, but you should imagine this is probably no more than a micron across, probably less than. So it's really zoomed in on the structure here. These filaments clearly appear to extend well beyond the cross-linking junctions between other fibers. Okay, so that kind of a meshwork is very important. Actin is an important, in some cases dominant, not always, mechanical, responsible for the mechanical stability of at least some cells. In muscle, by the way, I should point out, actin is essentially the same biopolymer that forms ordered arrays in our skeletal muscle, and in coordination with a molecular motor known as myosin gives us muscle contraction, okay? But even non-muscle cells have sort of disordered arrays of actin typically. Okay, so there's other stuff going on here not labeled, but I'll just introduce a class of important biopolymers known as intermediate filaments. Specific names are things like vimentin, neurofilaments, keratins. Anyway, they're interestingly apolar filaments. So although the monomers typically have some structure and not necessarily mirror symmetric structure, intermediate filaments as a class of polymers, probably the least studied still to this day of all three of these. But people have learned a lot about these over the last few years, and they're interestingly apolar. So they're arranged in a symmetric fashion, even though the monomers are polar. They're arranged in a compensating fashion. So these do not have a local directionality. One interesting implication of that is that there's no molecular motors associated with them. Okay, molecular motors is not the subject for today, but it's at least something that some of you may have heard about. Now, So this is already in the cell. At the larger scale, we also have extracellular matrices. Two important ones, well, the most important arguably is collagen. It's the single most prevalent protein in our bodies. Super important, not always, but often appearing in a structure sort of like this. This is collagen type 1. There's multiple types. Of course, we're talking about biology, so when I use a name, you should imagine that there might be multiple variants of it. Not just between different species, but even in the same species, there might be different types. Anyway, this is actually from a reconstituted collagen type 1 experiment in Gijsje Koendering's group by Karin Janssen. I don't have a scale bar here, but you should imagine the open pores here are more than an order of magnitude larger than what I just showed you, probably 2 typically. So these are more than a micron in size pores, typically big enough for cells to sit inside. And mixing images, the left is not collagen, but at least that image is nice because it shows the scale with respect to at least red blood cells. This is actually a fibrin or blood clot, really. So blood clots are not tissue, but they're tissue-like. And it's an important part of wound healing. And the nice thing about this image from the Wiesel group is that it shows nicely the scale here. Cells sit inside these matrices. So again, filamentous protein structure in a maybe isotropic, sometimes more or less isotropic, not always isotropic, but meshwork of some kind, okay? So these are systems I'll get to increasingly as we go along in the series of lectures, but I just want to show you already that there's some similarities. This image superficially looks a lot like the actin image I showed you before. In particular, there's nothing like a random coil here on the scale of separation between crosslinks, as you would have in something like rubber. Okay. So one of the first things I'm going to do is start outlining for you how to what the analog of things like the radius of gyration or random coil configuration and maybe entropic elasticity, what the generalization of those ideas or applicability of those ideas to these systems is. I'll start talking about single filament properties, but I want to already give you a sense of why we might want to try and model these systems or understand them theoretically. They're very different from flexible polymer systems as macroscopic networks. So not only do you have differences of local structure, but there's a characteristic response of tissue and even single cells, which is radically different from something like rubber. So this is actually from a collaboration years ago with Paul Janme, one of the people who got me first interested in biopolymers. We're still collaborating. And this figure shows nicely the contrast between something like polyacrylamide. Polyacrylamide is essentially a flexible polymer system. It's linear elastic, so this is the shear modulus. Shear modulus is ratio of stress to strain. It's soft, so we're talking about shear moduli less than a kilopascal. That's much softer than rubber. But it's flat. It's basically independent of strain. Notice the log-log scales here. Whereas all these biopolymers show a characteristic qualitative response, which you already know by pulling on your own tissue. Pull on your earlobe, and it'll stiffen. So it's roughly linear elastic initially, followed by a regime where the compliance basically goes to 0. And you can load it with much higher stresses than you would expect based on its linear shear modulus. And so that appears for collagen, actin, fibrin, that was the blood clot. Vimentin and neurofilaments are examples of those intermediate filaments. Different scales involved of strain and so on, but basically similar response. So it's a characteristic strain stiffening response that first started to get several people interested in understanding these as polymer, well, from a polymer physics point of view, if you like. Now, just to show you the generality in a little bit more detail, this happens to be from experiments a few years ago from Margaret Gardell when she was a grad student with Dave Waits. And it shows a series of different samples of actin. This is now, so because the systems are so nonlinear, it's basically a nonlinear stress-strain relationship, non-Hookean. It's no longer that useful to talk about the ratio of stress to strain. It's more interesting to talk about the derivative of stress with strain. So in other words, you take the stress as a function of strain and take its derivative. That's what's known as the tangent modulus, not the shear modulus. But it's basically the same idea. It's a local stiffness, so it would be like straining a system and at that level of strain asking what the resistance is to a further small deformation, okay? And so this shows, well, almost 2 orders of magnitude increase in the stiffness. But this is now plotted as a function of stress versus strain, rather than strain. And so that's actin, neurofilaments, vimentin. These intermediate filaments do it as well. This was some follow-up work in a collaboration with the same group. And here you see a full 3 orders of magnitude stiffening. So these neurofilaments in particular are going from a very soft, well, actually, what is the modulus? Well, here it's shown not normalized. So we're talking about nearly a Pascal. That's a super soft material. And then stiffening dramatically by 2 to 3 orders of magnitude. So understanding this has been one of the puzzles that has been, largely sorted out over the years. And I just want to show you an analogous result at the level of tissue. Now, this is from a classic physiology experiment of Fung years ago. And he did an interesting thing. So this is basically that earlobe experiment. Pull on a tissue, you extend it. This is actually Young's modulus measurement. Is basically just measuring the response to extension along one axis. And then he plots the force. And notice it doesn't look particularly Hookean. Doesn't look at all Hookean, really. And so I don't know why, but he did an interesting thing. He actually plotted not just force as a function of extension, but the derivative of force not versus extension, but versus force. So in other words, take the derivative of this curve, this force axis versus extension, and plot it versus the vertical axis, force. And he saw an approximate straight line. What function has that property? Exponential, right? This suggests a sort of approximate exponential stress-strain relationship. That's pretty weird. Now, it is approximate. This can't actually be accurate at low strains because there won't be, strictly speaking, it doesn't permit doesn't admit a linear elastic regime, but it does have a linear elastic regime, so it's approximate. And the other reason I like this experiment is it begins to point, it was actually the kind of thing that started making us think about the possibility of a phase transition. And that'll be mostly the subject of next week, although I'll start getting at that maybe later today. So if you think about stiffness as something you're interested in one of these networks, think about it like, and apologies to those who understand this already better. This is a simplistic way to look at it. It's an intuitive starting point. If you think of stiffness as an order parameter, like magnetization, think about this linear relationship between that and a load. That starts suggesting something like magnetization versus field, right? Begins to start to suggest that we should think about the mechanics in a sort of phase transition language. Just a hint for now. I hope to convince you of that later, okay? And, well, in a little bit greater detail, these are experiments, again, from the Klunderink group when her group was in Amsterdam. She was a colleague across town from me in Amsterdam. She's moved to Delft now. I moved to Rice, but we still collaborate. Had A lot of fun working with her over the years. But I like this image because, forget the dashed line for now. The open symbols are experiments on those reconstituted collagen networks. The image I showed you a while back, not quite tissue, but tissue-like. And it shows, again, almost 3 orders of magnitude, really a full 2 orders of magnitude at least, of stiffening at strain levels of about 20% to 30%, okay? We'll ultimately get to understanding that, okay? But for now, let me switch gears and start to look at a little bit more detail about the kind of puzzle suggested by some of these experiments on elastic properties of these networks. So let me begin by just plotting shear moduli or Young's moduli. I'm not going to worry about a quantitative distinction between those. I'm going to do this on a log scale, even multiple decades here. So this will be in pascals. Force per area or energy per volume happens to be an interesting way to think about moduli. So these are going to be engineering groups of 3 decades, okay? Hard materials typically have multiple gigapascal moduli, so steel is going to be up here somewhere. Interestingly, hard plastics are similar magnitude. I'm not saying they're as stiff as steel, but similar. Even protein. So the individual proteins that make up those, the globular proteins making up those fibers I was telling you about, if you were to take a concentrated, well, basically volume fraction 1, if you like, sample of that protein and measure its moduli, you'd get about a gigapascal, maybe 100 megapascals, but it's of that order. Rubber is here. Well, so 10 to the 3 is actually kind of an interesting range. I should say cells are sort of around here. And that's an interesting story in itself. People have tried to quantify mechanics of cells, and it's not quite as simple as having a single modulus, but if you'll allow me to take a sort of physicist's view of this, it's in this range, typically. So 10 to the 3 is about the modulus of gelatin. So like some things we eat, okay? 1 pascal is really soft. In fact, when you get down here, it's hard to measure. But like a colloidal crystal can be somewhere around here, pretty soft, okay? So other soft matter systems. Now, why is this interesting? Well, I just told you that cells, at least in some cases, have a predominant mechanical component, which is a network of these actin filaments. The individual actin as a protein is up here at about gigapascals. How do I get kilopascal moduli from a system like that? Well, I dilute it. Obviously, the actin wasn't filling space. But its volume fraction is about 1% in a cell, or about 0.1% in a lot of the reconstituted experiments, okay? So you might guess that you could take a shear modulus of the network and say, well, it's going to come from the shear or Young's modulus, I'll say shear, of the material making up the fiber. It could be, you could actually, by the time you get to collagen, you can almost think of it as little plastic rods, okay? Times a volume fraction. Okay, that would be a simple model of, and it actually turns out it would be the model of a nice uniform ordered lattice that deforms affinely. The prefactor would depend on the microstructure of the lattice, et cetera. But I told you that the volume fraction The volume fractions are of order 0.1%. That'll bring you from here down to about here if you're lucky. How do I understand that? So that's already an interesting puzzle. Basically, those networks are softer than you might guess. Now, there's two reasons for this, at least. But there's two directions to understand this, maybe. One is in terms of single filament properties. So I'll leave it as a question why that is wrong, apparently. Well, there's a single filament reason, which is those filaments are not just Euler elastica rods. They're fluctuating. They're thermal. Yes?
So the modulus of the network is about what, and the fiber is about what?
Well, so what I'm saying is the fiber, if you were to measure the protein, would be up here, 10 to the 9, 8 maybe. And so how do we get moduli down here? Well, this, by the way, this is a classic sort of material science sort of, actually, the name is escaping me of that kind of a model, but there are many systems that do this. I'm ultimately going to argue a much better approximation is to say it's proportional to the square of the volume fraction. But that's not what you'd get if you just took a bunch of fibers and arranged them on a nice triangular lattice or its generalization in 3 dimensions, sheared the system, you'd get a volume fraction, one factor here.
The square basically means that the proteins need to smush against each other in order to get you...
No, so jumping ahead slightly, one way to understand how it might be a stronger power of volume fraction and therefore weaker modulus is the mechanical response is not just to stretching the fibers, which is what you measure in a Young's modulus of the filament, but also bending. Okay? Turns out that can give you an additional factor here. But it'll take me a little while to get to that. Okay? So there's two reasons, thermal fluctuations. This is a single filament property. And the other one is it's going to sound a little bit like jargon here, but basically what I mean is non-uniform strain, or what's called non-affine. Affine being, if you shear a sample and every element within it is strained exactly the same way as the macroscopic strain you impose, that's what's known as affine shear. So a lattice would do that, okay? At least you'd expect it to. So this is a collective property or a network property. So I want to address both of these things, okay? And show you how we can understand basically how this is off by orders of magnitude. Okay. So let's start thinking about these single filaments. So I'll draw some filament fluctuating around, and I'll think about looking at the arc length along a filament and ask the question, what about how would I describe the shape of this? So there's a local tangent vector. Make it a unit vector, t. And if this filament is fluctuating around well before the point at which I get a random coil where it might, take on all different directions and coil up, as it starts to fluctuate laterally, it starts to wander. And so if I were to look at the distribution of all these endpoints, I would get an ensemble of points that would look something like that. Okay? Yep?
Could the temperature be an additional factor?
Yeah, thermal fluctuations is what I mean here. Thermal fluctuations, yes?
About polarity, what about charge? Are they
Oh, yeah, yeah. So everything is in essentially an aqueous environment. Almost automatically everything is charged. They're polyelectrolytes, actually. However, typically salt concentrations are very high to the point that the long-range interactions due to that are strongly suppressed. So the polyelectrolyte aspects don't typically play an important role at the level of these networks, where the relevant scale is, certainly by the time you get to a micron, let's say between crosslinks or the mesh size of a network. It might affect the stiffness. You might imagine a possible stiffening due to charge along the backbone, but again, even there, the mechanical rigidity is such that those charge effects are very weak. By the time you have a 7 nanometer wide filament, it's, yeah. But you're right, they're charged. I want to characterize the range of these fluctuations a couple ways. So this is going to start to look like the generalization of a random coil. It's clearly not a random coil, but I'm getting there, if you like, if I make this long enough. So I'll call the lateral fluctuations delta U squared. Obviously, they're equally likely both directions if I have a symmetric situation, if I don't somehow break the symmetry. So the quadratic, so the first order average here would be 0. I get, this would tell me something about the range of fluctuations laterally. I can also characterize the shape by some angle it makes relative to, let's say, some initial angle. And one of the first things that will, well, so let's see. Just to define some things here, obviously, the unit tangent vector could be defined in terms of the derivative of position along the fiber as a function of arc length. In a straight line, obviously, these would wind up being parallel. And the other characteristic is the curvature. So the curvature of this continuous curve could either be described in terms of the derivative of the angle, or I could take the following. If I take a derivative of the tangent vector and dot it into the unit normal, I would also get the curvature. Now, you start to have to be careful with that. That's a 2D picture. What about curving in different directions, right? So 2D and 3D are a little different. Question?
What is the formal definition of the vector arc?
Oh, it's just a position. So I'm basically just looking at the coordinate I want to use is arc length, S, distance along the curve, and the position of this point as a function of that just defines a curve. I'm going to be using partial derivatives basically because you should also imagine that all these things are time dependent if we do dynamics. So I'm only looking at the spatial parts. Okay, so this starts to begin to suggest a Hamiltonian or an energy for this system, which I should write this way. Okay, curvature, again, without a broken symmetry, curvature should be equally likely either direction. If I take the square of that, that tells me how much I've actually literally deformed the fiber in a way that's symmetric, curving up and down. So it's a harmonic-like term, if you like. I integrate that along the arc length of the fiber, and I multiply by a material constant, I'll call it kappa, the curvature, well, the curvature modulus, you could say, or rigidity. The units of this are, well, if this is an energy, angle is a dimensionless thing, I'm taking a derivative with respect to a length. This has units of inverse length overall. So this has units of energy times length. Okay, now I won't worry too much about subtleties about how to do this properly in 3D. I'll just stick to 2D for now. But what it begins to suggest is that I should be able to characterize these fluctuations in terms of this parameter, right? It suppresses bending. Yep. So why am I, other deformations I could stretch too, right? Yeah, I'll get to stretching later. This is actually what's called a worm-like chain model, essentially, and it's initially going to be inextensible. I will add stretching to it. So at some point, I'll need to add to this stretching, maybe. The reason I'm ignoring it is the following. When you have a thin rod, it's much softer to bending than it is to stretching, okay? So there's a nice separation of those two energy scales, if you like. Okay, so let's start characterizing these things. How would I expect these transverse fluctuations to go? This is not a real calculation, it's an argument to get everything except a prefactor. Well, so I've just argued that it should go inversely in the module, this bending rigidity, right? The more rigid, the less it's going to fluctuate. These should be thermal in origin. So I'll say KT over kappa. Kappa is units of energy times length, so this is an inverse length. How do I get a length squared? There must be some other length. What's the most relevant length? Well, obviously those fluctuations grow as I move further along it. So if my scale of interest here is, I'll call it L, then this should go like L cubed. Okay? That's how I get a length squared here. But unlike a random coil, there's multiple fluctuation effects we might be interested in. And again, I'm basically focusing on single filament properties initially just to see if we're modeling the mechanics correctly. And I will claim we're not by doing this kind of an argument. There's another thing that happens. Let's say as a straight rod, this segment here would have been that long. The thermal fluctuations laterally contracted and only contracted, assuming no extension along the backbone, by an amount I'll call capital delta L. Now, I'm interested in the thermal average of this because, of course, there'll be an ensemble. So I'm basically asking the question, how much, when I turn on temperature, does this cloud of endpoints shift to the left? Well, that's also thermal in origin, should be suppressed by bending. It's a length, so it should go like L squared. Yes?
I didn't quite understand why you said that when you turn on temperature, you only shrink.
Yeah, so if I'm not extending the backbone, sorry, guess it's, well, can you see this? Yeah. So if I deflect laterally, I only move the ends together, right? So it's strictly contracting due to fluctuations. Yeah.
Is it possible to consider a twist?
Yeah, so I'm not allowing twist in this picture. You can add it, and you might want to if the bonding between fibers is such that it might freeze in some twist. It tends to be a higher order effect. so I will ignore it for now. So there's also a torsion you could include here. One more fluctuation is actually particularly interesting, and that's the width of this. So I'll use a different symbol for that, little delta L squared averaged. So again, this cloud of points is characterized by three things: a thermal shift due to contraction by transverse fluctuations, lateral fluctuations. By the way, this is sometimes related to what's known as a wandering exponent. What I'm saying is that the typical displacement laterally as a function of length along the filament is the 3/2 power of the distance I move along it. So you can imagine a sort of trumpet-like shape growing. And then the third one is actually, I would argue, the most interesting from the point of view of understanding the mechanics, because if I know the range of end-to-end fluctuations of this, that'll tell me a spring constant, because I would expect those fluctuations to be governed by kT and a spring constant that suppresses those fluctuations, okay? And so let's look at that one. Now, I'd be tempted to start with the same argument here, kT, bending, et cetera. If I do that, I'm going to wind up with this same scaling, maybe a different prefactor. Now, that's fundamentally wrong, though. And the reason it's wrong is that the longitudinal displacement, because of this argument I was going through here, the longitudinal displacement is quadratic in the transverse displacement. Because if I deflect upward, I get the same contraction as if I deflect downward. So that means that these fluctuations have to be quadratic in these. So I get kT over kappa squared. And now to get my units right, I need L to the 4, I guess.
Could you repeat how do you characterize these fluctuations?
Yeah, so the end point of this fiber, which at 0 temperature, as a rigid elastic object, equivalently, would have been the straight line of this length. I turn on temperature, and as I increase temperature especially, these fluctuations grow. 3 things happen. The end moves in on average, but fluctuates around. The positions fluctuate laterally, so there's a cloud, there's an ensemble of points, if you like, that forms a cloud here. And that cloud is asymmetric. It is a sort of pancake shape. It's thinner this direction than it is that direction. And again, the interesting thing about this one is that should be kT divided by an effective spring constant. Because, well, basically, the average range for a Hookean spring, the average range of end-to-end fluctuations is kT divided by the stiffness. Okay? Now, that spring constant I could put into this picture of an affinely deforming network so that when I shear my sample, I take a filament here and I stretch it. And as I stretch it, that suggests that the mechanical resistance to that should come from this spring constant here. Now, one more thing to do before I actually calculate that. This ratio of kT to kappa is an interesting one. I said kappa has units of energy times length. If I take that and divide out by kT, take the ratio of those two, I'm left with a length. That's what's known as the persistence length. So naively, what the persistence length is is a range over which a polymer, even in the presence of thermal fluctuations, will appear approximately straight. That's the way to think about it. In fact, the more precise thing to do is ask the following question. How correlated are the orientations of a fiber along its backbone? And this winds up being e to the minus s prime over LP. And so that persistence length tells me essentially about the decorrelation of the orientation of the polymer. And so that means these expressions can also be expressed in terms of length. This becomes L cubed over LP. This becomes L squared over LP. And this becomes L to the 4 over LP squared. Now, let me just quickly sketch, and then maybe we take a 5-minute break. Yeah.
So you have free end boundary conditions?
Yeah, so good question. I'm suppressing some of the subtleties about the boundary conditions, I'm assuming. Boundary conditions will change the prefactors here. They won't change the scaling. So you could imagine different kinds of boundary conditions. Oh, here's another fiber. I could fix the slope at the two ends and then allow fluctuations. I could have pinned boundary conditions, so to speak, freely hinging at the ends. I could also have a free boundary condition and a fixed boundary condition. All of those will just wind up changing prefactors. I happen, in the calculations that, well, the most relevant calculation is the pinned boundary condition. Because think of those pins as coming from the cross-link points where the fiber's connected to the network.
The other question, do you make calculations for curvature fluctuations in the curvature?
Yeah, implicitly, yeah. So what ultimately, now I wasn't planning to go through it in detail, but would be happy to. Actually, I also sent a Reviews of Modern Physics reference article, which does some of this in greater detail. The right way to do the kinds of calculations and get all these prefactors is to do a mode analysis. So you break up the transverse displacements of the fiber and just Fourier series of the shape modes, depending on the boundary conditions. And then what you get are thermal amplitudes for those modes. And so that's basically a mode spectrum of different bending wavelengths. That's the right way to do the full calculation. The one full calculation I sort of wanted to do is to derive this thing for you. It's pretty easy. So this is probably the last thing I'll do to within a factor of 2, as opposed to a scaling argument. But so how does this work? So the other way to do this is also the average cosine of theta n minus theta 0. So what I've done is I've taken 0 to s, and I've broken it up into n segments, et cetera, up to n, not to be confused with that unit normal. So if I could get the average cosine of that angle difference, that would give me this, right? Now what I can do is I can just use trigonometric identities here to say, well, the cosine of, so actually the way, well, yeah, I'll just do it this way. So I could take the cosine of delta theta n times the cosine of theta n minus 1 minus theta 0 minus the corresponding sine expressions, right? Just a trigonometric identity. Now, one of these sines, though, is going to be the sine of delta theta n. So what do I mean by delta theta n? It's the angle difference between these last 2 points. Okay? Now do thermal averages. In fact, the deflection at the next deflection should be independent of the previous angle if I mean, apart from mechanics. They shouldn't be correlated. So then I can break this average up, and this one goes to 0, because it's equally likely to fluctuate up versus down. Now notice what's happening with these. I get cosine delta theta times a similar thing I started with, but it's 1 shorter. Dot, 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 continue. And what I get is the average cosine of delta theta to the nth power. Okay? Because I just pull out this factor. I do the same analysis here. I pull out another delta theta. It's delta theta in and delta theta in minus 1. But of course, as independent averages, those are the same, provided my fiber really has the same mechanical rigidity along the backbone. And so I just get the nth power of that. And what's that? Well, this is approximately, so this factor here is approximately 1 minus 1/2 average delta theta squared. Average delta theta squared I get directly from this energy. Once I do a discrete version of this, it becomes a sum of delta theta squared divided by delta S, the length of those segments, times delta S, summed up, times 1/2 kappa. But every term, 1/2 kappa times that combination has to be on average 1/2 kT, the equipartition theorem. So let me see if I got all my factors of 2 right. Yes. Doing all that, I find delta theta squared average is nothing more than kT divided by, kT divided by kappa, and I need a factor of delta S. Delta S is coming from the extra factor of delta S implied down here once I take it to the other side of the equation to evaluate delta theta. Plug that in to here, and my tangent vector decorrelation, or my correlation function, winds up being 1 minus kT over 2 kappa delta S raised to the nth power. And that's nothing more. If delta S is really small, take the limiting procedure here, and of course this becomes an exponential. Well, it's actually, the way I've done it is just S, because I started at 0 there. My S prime was 0. Divided by 2 kappa times kT. Whoops, this is not squared. So this identifies LP by this analysis, or by that definition there, as 2 kappa over kT. Okay? So far, so good. Why did I claim that it was only 1 power? Anyone see what's wrong with this? And then we take a 5-minute break. Remember I said I'm only allowing motion in the plane? There's another polarization. That doubles the rate of decorrelation. because fluctuations this way and that way both decorrelate. This is a 2D result. In 3D, it's kappa over KT. Okay, that's probably the last calculation I'll go through in that level of detail. These scaling arguments are sufficient. Yes?
You said that you use this partition energy to reach the gas. So my question is it, how good is the approximation given that you are in this biological medium?
I've assumed thermal equilibrium for now. For sure, we're going to want to possibly relax that, okay? I'm doing the analog of, as I said, the Gaussian chain, if you like, the thermal fluctuations of a polymer, but thermal. You're absolutely right to ask that, and maybe this is a good place to even go back to a picture, and then we take our break. Remember that picture there? If you try to estimate what the thermal persistence length of collagen is, it's a meter. So you got a nanometer wide object that would retain due to thermal fluctuations, would retain correlations over a huge scale. The reason for that, by the way, is the very large power of radius with which the bending rigidity depends on. It actually goes as the fourth power. So by the time you get to 100 nanometer wide filament with that kind of modulus of the structure, you wind up with about a meter persistence length. That image doesn't show anything like straight fibers on the scale of a meter. This is partly what you're asking about. I would argue the shapes involved there are not thermal. That system is effectively fully athermal, in fact, so rigid. But you have to distinguish a imaging persistence length from a mechanical persistence length. This is basically a mechanical one, although it's measured from thermal fluctuations. People do this experimentally all the time. There's very classic experiments going back to the 80s where people started to do this really quantitatively. They would measure, for instance, the persistence length of a microtubule or an actin filament by looking at fluctuations. And through the analysis, they would measure basically the decorrelation, infer a mechanical modulus. That can fail if your system is not thermalized. And it can fail for two reasons. One, what you're getting at, it could be out of equilibrium. Three reasons. Sorry, this is sounding like the Spanish Inquisition skit in Monty Python. Yeah, three reasons at least. It could be that there's actually bending defects. So I've assumed a nice homogeneous elastica, Euler elastica, nice uniform rod. It could have a bending defect. There could be a defect in the local structure of the polymer. It can certainly happen. You could have that it's out of equilibrium. Maybe it's being bent by other forces, non-equilibrium forces. The other one, which is more subtle, is dynamics. You would have to observe the fluctuating filament over a long enough time scale to fully explore all of its conformations. That winds up being very long when you start looking at a long filament, because the dynamics, I don't think I'll have time to get to dynamics, but the dynamics of this are very interesting and subtle. The rate of transverse fluctuations goes as a high power, like fourth power of the wavelength involved. And so you get very long relaxation times for long wavelength fluctuations. Yeah, and so you have to do the full mode analysis, look at the dynamics of each mode. You have to ensure that you're actually thermalized. It actually is better than it sounds because that also becomes a diagnostic. If you confirm that the distribution of bending modes is the thermal one for multiple wavelengths, you have more assurance that it's thermalized. Hang on, I just thought of a possible fourth reason. Again, I'm not ending my list of possibilities, but that's escaped me now. Anyway, I think that's a good place to, I guess you normally take a little bit of a break at this point?
Yeah, I mean, I think it's just for stretching.
Yeah.
So we'll do
So
like
it could also
a-
be questions. I'm happy
Yeah,
to.
let's all stay in the room. You can stand or stretch and ask questions, and we'll continue in just a few minutes.
Just an actual, I think I only now realize. So delta L is the width of this cloud.
Yeah, I'm characterizing it as a quadratic quantity, delta L squared.
Yeah. And okay. And
Sorry, hang on. No, this is the lateral, that's the longitudinal, delta L squared.
yeah. Okay. And why is it then proportional to
Ah,
that quantity?
because if I deflect upward, I get a contraction. If I deflect downward, I get a contraction. So it cannot, to linear order, this should be unaffected by that. So it has to appear at a second order. Equivalently, you could say, what gives rise to this contraction? What gives rise to that contraction is the square transverse fluctuations. And now if I want to know the fluctuations about that, it's a higher order fluctuation. Basically, I'm claiming that this quantity cannot be linear in that quantity. It has to be quadratic.
This one is linear with this one.
Yeah, this one is linear in that. This one is quadratic. Now, there is a full calculation you can do with all the modes. And when you do that, you will confirm this.
And
It's actually done in that Reviews of Modern Physics article.
I'm sorry, I have the same question. I don't understand the difference between this and this.
Yeah, so this cloud of points is characterized by three distinct fluctuating quantities. Obviously, the lateral one. Also, a longitudinal range of fluctuations. But in addition, because all transverse fluctuations move this endpoint to the left, there's an additional linear order average of the contraction. And so basically the cloud moves in by this amount, which is thermal in origin, fluctuates laterally by that amount, also thermal in origin, and fluctuates longitudinally by a fluctuation, a quadratic fluctuation that has to be itself quadratic in these. Because independent of the sign of u, I get the same sign of contraction. So that's why this has to be quadratic in that. The right way to do it is a fourth order correlation function, and then you do the usual average of four, Gaussian average of four things. Wick theorem, I guess, yeah.
And the second question is, the first pictures that you showed us for the moduli, are they different for compression and convection? So they were all.
There's a reason I'm focusing on shear. You mean this
Okay.
sort of thing? There's a reason I'm focusing on shear, and that is the systems, well, a cell, but also the experimental systems on reconstituted networks, they're always in a solvent. And the fluid itself is incompressible. So doing bulk modulus measurements of an elastic network given the presence of a fluid is not possible. So it's usually shear that people probe. Now, the extension measurements on tissue, that's done with free boundaries on the edges. So you just let the sample contract laterally. If it preserves its volume, you stretch it this way, it'll contract. Yeah, measuring bulk moduli turns out to be hard because they're all solutions.
I want to talk about how this will change if you consider the crosslinks and they slip through the crosslinks.
No, they're actually fixed.
They're
They're fixed.
Yeah.
Yeah, so ultimately what I'm going to do is I'm going to say the distance between cross links is the relevant length we need here.
Oh, okay.
Because that's where the fluctuations are constrained at the ends. And then that'll mean that depending on the distance between crosslinks, I get much softer networks because my modulus, so you see this spring constant is going, if I invert these, the spring constant is going like the inverse fourth power of the length. So if I separate the crosslinks by a factor of 2, the spring constant goes down by a factor of 16. So that's one way I can get a much softer network.
I want to ask you again about the scaling geometry for the fraction squared. So if we're doing shear,
Which I haven't yet done, by the way. I'm just hinting that
Right.
that'll happen.
but it does seem compelling to me to think that I'll get something which, if the deformations are non-affine, so why would these things mind if I'm doing some strain to the cell? They would only mind, I guess, if there is some overlap between them, and then it would be very natural to put the fractions.
Oh,
square.
you're thinking of like a two-body interaction.
Yes.
Yeah. So the volume fractions are so low that additional two-body interactions are negligible. Fibers rarely find each other. At 1/10 of a volume fraction, 1/10% volume fraction,
But then it's
they
a
actually
good
rarely find each other. It would be a good approximation, but it would also be a very weak effect. So the way you can get a square here is, actually, I think I'll actually go through that argument. So if you hold off, I'll get to that. Yeah.
What is the persistent length of typical spider web?
Oh, yeah. So spider silk, I don't know. The thermal persistence length should be huge, though, because it's I don't know the dimensions. Is it like 100 nanometers diameter?
I don't know, but the only thing that I know is that.
All right, why don't we grab our seats and keep going so that we can get to the coffee break at 11.
Okay, so I don't think I turned anything off here. I think it's all still going, right?
No, that's okay.
Yeah. Okay, so let me sketch for you how to do all these calculations more precisely and get the prefactors, okay? What's missing here will be various factors like 2s, 3s, pi's, stuff like that. Let me just sketch for you how to do the calculation properly, and it relates to the boundary condition question. Because I want to, I'll no doubt regret erasing this, but that's okay. I think it's easy to remember, right? So let me give you numbers. I showed you a bunch of biopolymers before. I concluded with this very, very important length, characterizing it with the caveats that it's an equilibrium quantity, et cetera. So what about numbers? And in particular, let's look at persistence lengths. Okay, well, I'll just say it in words. Polystyrene, flexible polymer, persistence length is effectively a monomer dimension, angstroms. Nanometer, 2 nanometers, small. By the time you get to DNA, which is, of course, a super well-studied and fascinating polymer on its own, happens not to be structural from the point of view that I typically get interested in, like networks. But so I don't tend to work with it a whole lot myself. But the persistence length of DNA is interesting. It's about, you could say, approximately 2 nanometers wide. And of course, can be a meter long, right? You probably know that. And this is, of course, ignoring all the interesting complications of histones and the way it's packed in the chromosome, et cetera. But just as bare DNA, which people study a lot experimentally, it turns out to be 50 nanometers. Now, that, by the way, there was an earlier question about polyelectrolytes. That, by the way, is just at the boundary of where, in a very low salt environment, you might start seeing some electrostatic effects. Because if you try to remove all the salt you can from water, you still wind up with a screening length, which is, you know, anyway. But it's huge compared with the diameter, which is more than an order of magnitude smaller. I mentioned actin. Actually, in order, I probably should say intermediate filaments. Shorthand IF. It's actually a huge family of proteins. Intermediate filaments. Those are the ones that I said were apolar. Very important structurally in some contexts for cells. These are about a micron. I say about because they're a family and they vary and so on, but it's of that range. Again, huge compared with the molecular dimensions. Actin's kind of an interesting historical story. I'll put 10 microns here. Now, again, its diameter was 7 nanometers. So notice that persistence length is now getting really separated from the transverse or molecular scale. And the basic reason for that is a mechanical argument, well, a dimensional analysis argument. If you say you take an elastic rod and you ask the question, for a given Young's modulus of this material, assuming it's isotropic and homogeneous, what would its bending rigidity be? Because, so if you stretch it, its stretch modulus would be that Young's modulus of the material times the cross-section area. The reason it's a stronger power with bending, though, is if I bend this thing, I'm stretching the outside and compressing the inside of the bend. And so that gives you 2 extra powers of length as it happens. But dimensionally, you can say this should go like the Young's or shear modulus of the protein times, well, this is an energy per length, sorry, this is an energy per volume modulus. This is an energy times a length. So there have to be 4 factors of length, and it is naturally the diameter or radius because it's a local quantity. It knows nothing about this other scale about how long it is, right? That's the only length it could be. And it's that strong dependence there that gives you this huge range. And just to give you a irrelevant number in practice, but just to make a point, collagen, type 1, those thick fibers I showed you, this would turn out to be about a meter. Oh, actually, I'm leaving one out, microtubules. Those green filaments in the first image I showed you, they're already macroscopic in terms of persistence length. It's a persistence length of a millimeter, even though their diameter is 20 nanometers. So now you're getting it, 5 orders of magnitude. And the reason I say the collagen one's irrelevant, the thermal fluctuation effects of those thick fibers are essentially negligible at this point. So you'll never see that idealized thermal one. Okay, so now let's put some things together and start sketching how these pictures can start explaining, at least initially, that puzzle about the low moduli. Remember I said the moduli are lower than you might imagine. Yes?
I'm still quite struggling to understand the fundamental meaning of the persistence length, especially
It's good to be puzzled by it because, in fact, it is subtle. Yeah?
Especially when you say when it's high or low, but especially when the persistence length is higher than the system diameter. For example, for collagen, what does it mean like it has a persistence length on 1 meter?
Well, okay, so what I'm really saying is its modulus, its bending modulus is so high that if you were to have a 1 meter long fiber of collagen and nothing else in a solution, it would just barely start to decorrelate the orientation of its ends due to thermal fluctuations. So the persistence length is kind of a imaging quantity. It's a sort of, it's inferring the mechanics and the mechanical rigidity of an object based on the shapes you see. And that becomes irrelevant in a couple of different limits I mentioned. Maybe you're not looking at the filament long enough to explore its conformations, or maybe its conformations are controlled by something else, like other forces. So it becomes a very idealized concept at this scale.
So is that a theoretical prediction?
Well, it's, I wouldn't even call it theory, it's just putting in the numbers. If you take the known Young's modulus of collagen that makes up a fiber, and it's in good agreement with some experiments that people have measured. By the way, as is true with a lot of things in biology, the error bars on these experiments are typically big. So a lot of these things are only known to within an order of magnitude, which doesn't sound great, but you know, that's life, or biology at least. They can be measured. So I'm just taking that Young's modulus and the expected bending rigidity and inferring what would be the thermal persistence length from that, even if it's maybe never observable. Okay, so now how does this start explaining things? At least that one of those puzzles I mentioned. So one of the first things to think about when thinking about network properties is I naturally have several length scales. If you take a flexible polymer, basically there's two relevant ones. There's a radius of gyration, how big the polymer is when it's fluctuating around, and then when you have a collection of these in either a network or a solution, there's what's called the correlation length. Basically, essentially, what's the distance between typical interactions of distinct polymer versus itself? Anyway, for networks like this, we have a couple of things. We have what I could call a mesh size. So this is what you'd see in an image. It's just the typical spacing between distinct filaments. Says nothing about how they're connected. Now, how they're connected brings up another length. Maybe there's cross links at these two junctions, so that I have a distance between cross lengths, LC, which, by the way, can never be smaller than that, because, of course, it doesn't make sense to cross-link a polymer to itself. It's got a meaningful cross-link as a cross-link to someone other than yourself, so to speak. So this relationship should hold. Now, the relevant regime for the kinds of networks I've been telling you about, though, is where that length is typically small, sometimes much smaller than the persistence length. So this could easily be much smaller in many cases. So the image I showed you of actin had mesh size of about 100 nanometers or less. That's a good 2 orders of magnitude below this. And in that structure, depending on the formation of that network, it's easy to have at least an order of magnitude difference between the persistence length and the distance between cross lengths. There's another length which I'll just draw as, in most cases of interest, typically of order, the polymer length itself. Distance between crosslinks. So it has, if you like, is a characterization of how constrained the network is. A crosslink forms a constraint where two otherwise free to separately move fibers are connected. That connection typically will occur on a scale larger than this by factors of 2, 3, 4, something like that.
So what is the mesh if the mesh is not?
Mesh is just like in an image.
They are actually above each other. You cannot see it in the picture.
Mesh would just be the typical spacing between fibers there. It knows nothing. So if I take an image.
They are separated in.
Yeah, so this is actually, this is actually a image probably on a surface where the system has actually been collapsed. So maybe that's not a great example. But people can also do confocal imaging of a full 3D mesh, provided that the spacing is not too small. And so it would just be the typical spacing between fibers, but that doesn't say anything about whether they're connected or not. Yeah, so some of the apparent connections in that image could just be that two fibers have crossed near each other, and I can't tell whether they're connected or just above each other, one above the other. That actually turns out to be experimentally a tough thing to do.
What is the mesh when the fibers are not parallel?
Sorry. This was a super highly, no network no disordered network would look anything like this, right? So you should imagine that these are all more disordered than I've shown.
But what is then the mesh?
Yeah, so it would wind up being some sort of average over the system of the spacing between adjacent fibers. Because depending on the orientations, I could have points where they get pretty close, points where, actually, in this image you can see the pores are very polydisperse. Some are widely separated. So a realistic definition of the mesh size would be to take that image and just say, if I take colloidal particles of a certain size, at what size, with probability 1/2, would it be able to make it through the mesh? Okay? Yes?
I wonder, you could also parameter control in your system. If you consider your string like a charged string, charged electric density, you put an external field. You know how this external field you affect your production function?
Yeah, so certainly if I have a charged backbone here and I were to apply some sort of field, I might radically change the conformation of the polymer. There's, the main reason I'm ignoring that is because typically the mesh size or the spacing between fibers is going to be of order hundreds of nanometers. It's hard to get long-range electrostatic effects in an aqueous environment, particularly when almost everything in biology is at high salt. High salt from the point of view of screening. So the Debye lengths, I don't have a good number off the top of my head, but they're going to be down in the nanometer range. So that's teeny compared with the spacing between fibers. Or given polymers that have a natural persistence length that basically keeps them straight on the scale of a micron or microns, again, electrostatic effects will be weak. So typically, it's a high salt environment, and electrostatics is screened out. It could be an interesting experiment to do or a question to ask, but it would be at least beyond the point of, well, it would be an effect which probably doesn't control the mechanics of the systems I'm describing. Okay, so let me just sketch for you the right way to do these kinds of calculations, and I'll show you one result to end on, And I think that'll be a good place to wrap up. Yeah, L. The length of the polymer itself. So depending on the preparation, the polymerization of your sample, you might have longer or shorter. You typically have a distribution. So although this is a length, I'll refer to it as a molecular weight. In keeping with the polymer language of molecular weight. So it's basically, it's not, you know, a mass, like a molecular weight, but it's a characterization of how much polymer there is. And length winds up being the natural one. So typically this one, well, obviously I wouldn't be talking about a network if that length were smaller than this. So it's typically a good order of magnitude or more beyond these scales. So what I'm trying to get at is the following. This cross-link distance is a really important one if you want to look at the mechanics. Because as I said, that's representing constraints. So ignoring the precise details of boundary conditions, you can think of those constraints as pinning the points on the polymer separated by that length. That winds up being relevant for this picture here, ultimately telling me about the stiffness of that segment. If I've got thermal fluctuations of the ends that cover a certain range, that implies, through this kind of a picture here, an effective stiffness. And that is the mechanical thing you couple to when you shear a network. If I've got some polymer oriented like this, let's say, and I shear this system, I'm asking to stretch this. And depending on the range of those thermal fluctuations, I have a stiffer or softer environment. And so let me turn this last relationship around here and point out that the effective spring constant, or I could call it thermal, this is not to be confused with kappa, winds up being of order KT LP squared divided by L to the fourth. That L to the fourth is key. Because if I can somehow control the distance between crosslinks, the density of crosslinking in the system, that changes these independent segments that are fluctuating around, the size of them, and that makes their stiffness go down dramatically as I increase that. This mechanism, a thermal softening, if you like, of the filament relative to pulling on its backbone directly, can certainly account for, well, what's erased now, but that missing 3 or 4 orders of magnitude between the naive estimate of the modulus of a network and its, the measured modulus. It's a thermal mechanism. I pointed out that there are 2 mechanisms. That's the single polymer mechanism. I'll also talk about a network mechanism, okay? But I think that's a good place to wrap up, but obviously still have time for questions.
I'm curious, if you removed all the crosslinks altogether, you might still get constraints from the mesh size.
Entanglements.
So how would that look like?
Yeah, so that's a very interesting question, and I won't be doing justice to several colleagues who've worked a lot on solutions over the years, including theories of those. It turns out these really are networks. So while the crosslinks themselves might not be truly permanent, there's actually a lot of what's called transient crosslinking, which is an interesting subject in itself, because then you have an additional stress relaxation mechanism. But basically, a solution of something like actin filaments is something a lot of groups were working very hard to study very carefully, experimentally, and then also develop theories for 20, 25 years ago or so. And it turns out to be really, really tough to remove the crosslinks. The reason is basically the actin is obtained, well, for full disclosure, harming animals is involved. Actin for most experiments is obtained, or at least by my colleagues, is obtained from rabbit muscle. So it's literally, there's a protocol for extracting the actin from muscle. Even though it's muscle actin, it does form networks similar to these non-muscle systems. So anyway, what people do is they take a tissue, extract the actin, and then reconstitute it and study it in some controlled environment. And, you know, physicist that I am, I tend to look at the experiments that do those controlled environments and reconstituted systems, and the experiments I showed you are exclusively those, except for the tissue one I showed. So here's the problem. There are literally 100 or more known actin cross-linking proteins, or associated proteins that somehow affect the stability of the network, or severing. So there's also severing proteins, turns out, that sever the actin. Enzymes, actually. What I'm getting at is the following. It's actually very tough to create a idealized filament-only, no cross-link system. If you do that, however, you can still get entanglement. But the entanglement and this is an interesting and very clear difference from flexible polymers. If I have two flexible polymers forming random coils, and I form a meshwork, this polymer here is randomly coiling around, and by the time it reaches another polymer, if it at all crosses it, it's likely to coil further, and I've got a pretty significant entanglement, okay? So that if I shear this system, I'm really stretching a Gaussian chain between these 2 points, whether or not they're cross-linked. Think about doing that with a fiber that's nearly straight in a low volume fraction. I can thread a network, or I imagine, well, for knitters in the audience, think about putting a knitting needle into an even dense collection of yarn. You know, I can actually go pretty far before I hit something, particularly if I dilute that system, okay? So entanglement alone in a semi-flexible or stiff polymer network is much, much, much weaker than it is in a flexible system. And so the corresponding moduli are a good 2 orders of magnitude typically below the cross-linked systems.
Well, I guess my question is quite related to this in the sense that I'm curious about experiments because, yes. I mean, the length scales, the persistence length that you are mentioning, is it from experiment? Is it from an isolated DNA?
Yeah, all these numbers come from literally doing the following kind of thing. I don't think I have an image handy. Let me quickly see if I do. If not, I could show you one in very short order. Actually, I think I can write. Okay, it's not exactly what you want, but it's close. Okay, now that is from fun collaboration many years ago with Paul Janme again. But what this shows, and it's got a scale bar. These are real actin filaments, fluorescently labeled. What people do typically is they take an isolated actin filament, fluorescently labeled, and they watch it fluctuate over time. And from those fluctuations, they do some sort of image analysis to extract this. And then they get that. So provided you're careful and you observe it over the right time scale for reasons that I mentioned before, the long relaxation times involved, you can get these numbers, provided that you're operating in a range which is observable optically. So basically we covered these. Microtubules people could do these measurements too. You have to be even more careful, but it's doable. So I would say all of these can be addressed that way. Now, there's a problem with that, though, and people have discovered this over the years. The The textbook number you'll find for actin is 17 microns. Very precise measurements. Happens to be with a fluorescent label. And it's now known that that label changes the persistence length. Okay? So the generally, this is still being debated, but I would say the realistic number, putting together lots of things that observed over the years, is probably more like 5 microns unlabeled. It's actually worse than that. The label turns out to be phalloidin, a toxin, and all sorts of, chemistry is involved. But that begins to show how complicated it can be to get that. And so you'll find multiple papers disagreeing with each other. You'll see at least an order of magnitude range on microtubules to this day, let alone trying to measure that in a cell. Okay.
Yeah.
Full disclosure, that's a network. It's a fractional fluorescently labeled polymer. So actually what you're seeing on the side here is a sketch approximately to scale of the mesh size. But this is the kind of experiments people do.
I think we need to give
Yes.
people a chance. So let's thank Fred again. And we start up again around 11:30.